Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this truss using in finite element analysis using Salome meca. So the material for this truss is steel I have taken. We are going to do linear static analysis. So the model is given here. First we'll model this using Salome meca. So just open Salome meca. Salome meca is the wonderful free and open source software for finite element analysis. So now it's got opened. So now see the model. To create this model using a line, we need a coordinate. This coordinate we have 0 0 and this coordinate we have x5, but this coordinate we don't have. Instead they have given angle 60 degree and 30 degree. So we can get the value by calculating, applying Pythagoras theorem. Otherwise we can directly go for that one more model called shaper. Just go to shaper. Now just go to sketch, start sketch. Here we can choose which plane you want to create. I want to create it in, just rotate it. So you just see which plane you want to. This is XY plane. I'm just choosing XY plane. Set the plane view. Now plane view is came. Now here we can create. So take the line directly. So I'm just modeling it randomly. Now I have done. So these two angle is 30 degree and this angle is 60 degree. Now we can set that one. Here there is different options. You can see it here. This is angle. This one is 30. Similarly this one and this one is 60. Now we have done. So still it's showing red color. That means that it's not fully constrained. For that there is one more option, is the horizontal, that is we are not specified it yet. Select this one, specify it. This one is 5. Now still it's red color. That means that still it's not specified this full coordinate. The final one is point constraint, middle point. Sorry. So distance from this point to this point, distance is 68 it shows. I'm specifying this into 0 or some value also we can give. So I'm specifying that value into 0, enter it. Now see, it's fully constrained. Fit screen. Save, okay. Enter. So its constraint is conflict with others, it's showing. Undo it. Now we can move. Keep this into inside. This also you just keep this into inside. This is 60. This one is 30. Now we can middle point constraint, this point, not this one. There is option called coincident. So just click this coincident, this point and this point will make it constant. Now you see this is completely got green color. That means our sketch is fully constrained. Now we are done. If you want to extrude, we can extrude, but our safe is just simply a line. So we can export this file. Go to file, export into a CAD format. So now just select this file. Now we need to name it. So I'm just choosing Vengat Pictures Code Aster truss. This is second case. I'm just saving this into truss 1 2. So this is the name. Just now select this file. So this is a sketch. Now you can see it here. Apply, just apply it, then only it will save. Now just go to the location, truss. The new file is truss12.bref. Bref is nothing but boundary representation file. If you want to save it in step file, IGS file, you can save it. Now I saved it into bref file. So now we will open this bref file into geometry model. Just move into geometry model. Now we are in the geometry model, so this will not be enabled here. Now just go to file, import bref. Now just go to the folder where we have saved second case, the first one, open it. Now see, so only this is a model we have created. This will come in a face file. So now what we can do, we can export a line or wire from the face. So wire, not the create wire, go to here, explode wire, apply and close. Now right click, so only. Now we got this wire. This is we wanted it. So now we have created the geometry. Then we can go for creating groups. Right click here, create groups, line, select all. So 1 2 3 line is there, that's why 3 number is coming here. Now this is actually truss. Apply. Now go to the model. Here simply supported, they have mentioned it. So what I'm going to do it here, I'm going to fix it. Here I'm going to give roller support. So choose this point, this one, add, this is fix, apply, select it here, add, this is roller, apply. There is one more point here, I just want to apply load. So this point you just choose, add, this one is load, apply and close. Now you see, this is truss is nothing but complete truss model. Fix, I just want to fix it here, I just want to give roller support here, I just want to apply load here. So every groups are I have created. So we can save this file, save it, truss. So location is code aster, trusses, second case, I'm just saving here. Now I have saved it. Now we can move into meshing. Mesh, create mesh, choose wire. Now you see 1D and 0D are enabled. 1D you choose wire discretization. Here gear button, just go to local length. This one you specify into 0.2. Say OK. Say apply and close. Then right click this one, compute. Now we have created, there are 60 edges and 60 nodes. So this one is, if you want to see the nodes, go add node. So our model is divided into nodes like this. Just close. Now we can save this file. Similarly, we are imported mesh into here. Now what we are going to create a setup using aster study. Now just go to aster study. OK. So just go for new stage. The first we need to read the mesh. Go to read mesh. Mesh, choose mesh 1. This is our mesh in MID format. Apply, save OK. Now we have read mesh. Go to model definition, assign finite element model, finite element. Here we can use everywhere. Mechanic, this is actually a beam. We can use So this is a beam element. These are all beam elements. PODE is an Euler beam element. This is Timosiki beam element. I'm just going to use Timosiki beam element. PODT, just say OK. So nothing need not to enable, just apply it, say OK. So beam element I have assigned. Now what we need to do, we need to define the element property. That name is Afikara element property. This is beam element, poetry, edit, section is the rectangle section. So two things we need to do, height and width. Similarly, two things we need to define, height is 0.1, width also 0.1. So we need to assign it to the groups. For that, go to group of elements, edit, truss. So here we have to create this truss. Say OK, say OK. Then here just scroll down here, this is the model, apply it, say OK. Now we have created the section also. Now just go for material. The first two we have done, go for material. First define material, then we need to assign material. Define material, linear isotropic, Young's modulus is 210 e power 9, Poisson ratio is 0.3, say OK, just apply it, say OK. Now you say we have created the material, we need to assign the material to the mesh. Go to assign material, we need to assign to the mesh, model, just click it here, edit, assign it to everywhere, click it here, material, say OK, just apply it, say OK. Now we are done. Now functions, in this case it doesn't require any functions unless just go to boundary conditions. Go to boundary conditions, assign a mechanical load, just keep it load. We need to enforce the degree of freedom. Go to enforce the degree of freedom, here edit. So where we need to enforce it, we need to enforce it's a nodal group. So we have the fix as a nodal group. Choose this one, edit, fix, say OK. We need to fix all displacement and translation degree of freedom. So make it 0. So we have fixed here. We are applying fixing boundary condition here. Say OK. Similarly, one more we need to add, edit. We need to give roller support here. That means we need to arrest all the degree of freedom. Here we have fixed it anyway. So here we need to give, it has to translate in X direction. So for that, group for modes, edit, roller, say OK. Here it has to move freely in X direction. We can arrest in Y, Z direction. So these two things we can give it 0, 0. Say OK. Just now we have arrested here, we have given roller support here. Now we just want to apply load in this point. The same there is, scroll down here, there are connections. Here there is a force options. Just go here, the force is 5 kilonewton, that means 5000 Newton. Here there is an option called force nodal, force on the face, force on the node. Just click, activate this one, just click this one, edit, choose the node group as load. See here, just say OK. We want to apply load in Y direction and minus negative 5000. Say OK. Now scroll down here, there is option called model, just apply. Now see, this is the command it will generate at the bottom, at the back. We are fixing one side, we are applying roller support, we are applying load, everything. Say apply, say OK. Now we have defined the load. Then pre-analysis, we need not to do any pre-analysis for this case. Go to analysis. Under the static, see static mechanical analysis. Choose material, choose element property, choose model. Go to loads, edit. We need to activate this load. Say OK. Then you just apply it. So this is the solver. Meca static is the solver. Say OK. Now we have defined the solver. Then we go for force processing. Call champ. So activate. This is actually beam element. So for beam element, just go here. What are the output? We can take it out. So beam element in code aster. So this is the beam element. See, these are the things for beam element. So we can include this SIPO node and SIPO node. So in last case we can check. Go to pictures, code aster, trusses first. So SIEF no, SIPO no, SIPO node. This is enough. Then reaction nodal. So this is for reaction force, to view the reaction force. So the same thing we can generate here. So constraints. So SIPO no for beam element, SIPO node. So then the force, reaction force. This is enough. We can switch on this model, material, structure, element property. Just apply it. Anything if you want to add extra. So EFGEL no, SIEF no. Just go here. One more. SIEF no. In deformation, you just go here. EFGE node. Not here. This is not energy criteria. There is no equal stresses. Here it's there. So just add it one more. There is EFGE no. So EFGE no, SEF no, and SIPO no. These are directional stresses and bending stresses. It will come in element and node. So and this force is a reaction force. just apply it, say OK. Now we have defined the output. Just here you see unnamed, just name it as same name, you just give wrestling, just apply it, say OK. So now we have done output post processing also. This is just leave it, just go for output, save the output, set output results. Here just click it here, go to pictures, so code aster, trusses, second case, result.rmed, just save it. Now just go here, just edit, you just make this thing enabled. There is one more option called toucham, just that also you just enable it, save OK, format to make it med, just apply it, save OK. Now see everything we have done. Now we can solve this problem. Just go to history view, save it, click this one, make this into 5 seconds, run it. Now you can scroll down. Now see, now it has done and the results are saved properly. If any error comes, we can view the message file, we can rectify it. If any error comes, it will show the error message. From that we can rectify it. Now we can go for post processing using paraview. Just open paraview, right click open, go to Vengat, pictures, code aster, trusses, the second case, our result file is result.rmd, just open it, then just apply it. So this is our model. Now you just choose the displacement. Now we are applying the force here. Similarly you just go for reaction nodal. So these are the reaction forces. So if you want to view the value in a particular node, so we can view it. So that is, just go to view, toolbar, Windows, there is a option called selection display inspector. It's already enabled. Just scroll down here, here. So here there is an option called selection display inspector. Make this into which one you want to inspect, you can choose it. This one you choose it, displacement, I have ticked it. Now whatever you are selecting it, it will show the displacement. This is a displacement plot. You just select the node. What is the displacement here? It will show. I just want to select only one node. Just go here. Only one node, choose it. So this is the displacement. This is displacement x, y, z, drx, dry, drz. That is the way it will come. So this is a displacement in x direction. You just see the displacement in y direction, it is more, because coming down we are applying force downward direction. So this is value is more. So similarly, if you want to see the displacement in reaction force, just scroll down here. So here, go to reaction force. We are in the reaction nodal. Now select the reaction force. Go to selection. This point. This is the reaction force. Choose this into reaction nodal. Not record anyway. This is a color pattern. You can see it. So reaction at x direction here is 0. But reaction in y direction it has more. Because we are applying y direction force. There is a reaction in y direction. So there is a rotational reaction also. Similarly, we can see the reaction force here. Select the node, this node. See, so there is a reaction force in y direction. This is a reaction force. So if you want to see the stress, go to zip. So just this one you remove it. Now if you want to see the stress, this first one is the stress value. The SN is a normal stress in the member. For any point, if you want to know what is the stress in this point, 0 stress. Similarly, stress here, all are 0. Similarly, we can see the stress here also. So these are not stress actually, these are reaction nodal. If you want to see the stress, you just go directly in this one. See, every point there is a stress. Normal stress in X, bending stress. All the values are there. This is a normal stress. Similarly, you can see the stress here. This is a normal stress. If you remove cross-sectional area, you can get the reactant force in the member. This is stress actually. If you remove it, you will get the force in the member. So this is a way we can view this color patterns also. So if you want to see the stress, just go and check the color pattern, just making this into rainbow, apply, close, and taking it. So this is a way stress. The stress is more in this member, which is tensile stress, because it's start to elongating, tensile stresses. And this member is getting compressive stress, and this member is getting also compressive stress. This member only getting tensile stress. So this is a way we can see. Same way we can check the value also. In that we have completed and we have completely analyzed this truss member using code aster and with using finite element analysis. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.